what I would like to do today is go through any questions you have with them. We'll review how to analyze satellite motion. By equating the net gravitational force to the acceleration of the object in a circular path. And then what we're going to do is you're going to use some time here to polish up your Flying Pig lab. I also have assignment number 4, which I'm going to give you. And then as additional practice, we can also work on these textbook questions. Yesterday, though, we started off by talking about the fact that the planets do not move in perfectly circular orbits. And the equations that we use, things like centripetal acceleration equals v squared over r, assumes that this speed of 2 pi r over t is constant. And the only way the speed of the planet or the satellite is going to be constant is if it's moving in a perfectly circular path. And I told you yesterday that the planets do not move in perfectly circular paths. And I mentioned something called eccentricity, and I'd like to spend a few minutes today to begin with talking about eccentricity. So this is a diagram showing the orbit of the Earth. And if I were to ask you, what shape is that? I think everybody would agree it's a circle. But it's not a perfect circle. And if you track the number on the right-hand side where it says currently, that's the velocity. And you can see that the velocity when Earth is on the right-hand side of that diagram, the velocity increases to about 30.3 kilometers per second. Obviously, this is scaled time-wise, right? It takes the Earth a year to go around once. And I'm going to, they've chosen a very bad color there for the planet, so I'm going to kill the lights so you can see it maybe a little better on the other monitor. But you can see as well, if you track the speed, that it's fast there and then it's a little bit slower on the other side. And what that tells me is that when Earth is on the left-hand side of the sun, the bright yellow dot is the sun, it tells me that when the Earth is on the left-hand side, it's further away from the sun rather. And my reasoning is if it's further away, the force of gravity is less, so it's not accelerating as great. And in fact, you can see the distance from the sun changes. It goes from 0.98 AU to 1.02 AU. AU is called an astronomical unit, and it is the average distance from the Earth to the sun. So this is a little bit elliptical. Now, I don't know if you can read from your perspective where you're sitting what the eccentricity is. The eccentricity is 0.017. No eccentricity, zero eccentricity would mean it's a perfect circle. So if I were to take a look at some of the other planets, well, I'll start with the planet that's closest to the sun. I think it's pretty clear. I don't know if it's clear that it's not a circle, but it's pretty clear that the sun is not in the center of this orbit. And as a result, since the sun is really, really off center of this orbit, if we want to use the word center, we can, you'll notice that the difference between the minimum and maximum speeds of Mercury is quite significant compared to the difference for Earth. And this is elliptical with an eccentricity of about 0.2. And I don't know, if you're looking at shapes from an angle, it's hard to tell. But when I'm looking at this dead on, even if that yellow dot were not there, I would be able to see that it's slightly flattened. Would you agree from your perspective? I think so. So that's Mercury. And you'll notice that we call the semi-major axis the distance here, but for Earth it was 1 astronomical unit. Here it's 0.387. So that's almost, it's like the radius, okay? It's the average distance between Mercury and the sun. So if you were to take the distance from Mercury when it's here to the sun and add it to the distance from here to the sun and then divide by 2, you get what's called the semi-major axis. And it's like a radius. It's like an average orbital radius. Of course, as we go out to Venus, Venus is further away from the sun, so you can see that the average radius, the average distance away from the sun of Venus is 0.7 astronomical units. Its eccentricity is even less than Earth. Like, you would be hard-pressed to tell that's not a circle. We go to Mars. Mars has a pretty decent eccentricity. It's almost 0.1, not quite. And as a result, the difference between the speeds becomes more significant. So as the eccentricity gets bigger, what's going to happen, and I'm going to cut to one here that I'm pretty sure is, let's go Neptune. No. Pluto? Pluto has a pretty high eccentricity of 0.25. I think you can tell it's quite flattened. But look at how slow Pluto moves when it's far away from the sun, and then it really picks up speed. Now, you want to be careful about something. The speeds of Pluto, if you look here, are between about 3.6 and 6 kilometers per second. Pluto moves a lot slower than Mercury because Pluto is already so much further away from the sun. Right? But when you compare the difference between the minimum and maximum speeds with something like Pluto, you discover it's fairly significant. It's going at the maximum speed, it's traveling almost twice as fast as it was at the minimum speed. If we take a look at a planet, not a planet, at an orbital like Halley's Comet or Halley's Comet, which takes, I believe it's about 76 years to come back into our solar system. Like this little section, I'm going to see if I can capture something. I don't know if I can. But this little tiny section in here is where all the planets are. Right? And the sun in this diagram you're looking at right now is drawn way too big. It would just be a point of light. When you look at the distance in this, and I'm going to have to refresh this. When you look at the distance with Halley's Comet, like this distance is 10 astronomical units. We're talking here about Halley's Comet being very, very far away. I think the last time Halley's Comet was in our neighborhood was 1987. So you will probably in your lifetime see it again. I remember being on a flight and looking out the window. The pilot told us to look out the window and we could see it. You could just, it's amazing because I'm going to speed this up so we can find out. Well, the maximum speed when it's close to the sun is 54.4 kilometers per second. And close to the sun means it's close to the Earth. But when you look out the plane window, when we looked out, we could just see it. It was like it was painted in the sky. It wasn't moving because it's still very, very far away. So I hope that gives you an idea about eccentricity. The more eccentric an orbital is for a satellite, the less we can predict with what we've learned in this class, things like how fast it's moving. So when you find, like in the problems yesterday, we found two basic things. We found the speed. What you're actually finding is an average speed. But when you find the period, you are finding the correct period with Newton's laws, even though it's not a circle, as long as you use the average radius. It's not even really a radius, but the average distance. And if you do that, Newton's laws and the work we did yesterday are pretty much bang on. There's not a lot of discrepancy. Obviously, as well, the work that we do in this class is limited in its scope because, you know, when you take a look at Jupiter, Jupiter has a whole bunch of moons orbiting it. And that affects the gravitational fields involved. There are other planets. And it's amazing that our solar system is able to function with all these orbits because every time some planets get closer to other planets, they influence each other. So these orbits are always kind of changing a little bit from time to time. But it appears to be kind of self-correcting. All that being said, now let's go back to the beginning here. What we say is that for an orbital satellite that's moving in a circle, the gravitational force is the net force. This is the net force. And we can write MA, which is net force, equals GM over MM over R squared. We can change that to the mass of the satellite times V squared over R equals G, mass of the satellite, mass of the central body over R squared. And that's how you develop a formula like V squared equals GM over R. Just a couple more quick things, and then we'll see if you have any questions from yesterday. In addition, once you know V, of course, you can use this formula to find T. If you want to find the time, though, you can do so directly because instead of writing for FC equals FG and following it up with MAC equals GMM over R squared, what you can do is put M times 4 pi squared R over T squared equals GMM over R squared. So you could find the time directly this way. And we saw with the final example yesterday, which is a geostationary satellite, that if you know the time, this is the key idea here. If you know the time and you want to find the radius of orbit, this doesn't work. Because when you take a look at the bottom formula here, time isn't even in it, first of all. And secondly, you don't know the radius and you don't know the speed. So the only way to find the radius from the time is to do that. Let's go over the questions. Then I want to talk about geostationary satellites and a very cool technological idea that people are thinking very seriously about. Does anybody have any questions you would like me to go over from the work? Go ahead, Ashley. Okay. So an artificial satellite, and you're given the mass of the satellite. What we've learned is that typically speaking, you don't need to know the mass of the satellite because it cancels in our work. But sometimes it might be useful. It's put into a circular orbit around Jupiter, and you're given the mass of Jupiter and the radius of Jupiter, and it has an orbital velocity that's given to you how far above the surface of Jupiter is the satellite. So regardless of the strategy, it starts off with, regardless of the specifics of the strategy, it starts off with net force equals the gravitational force on the satellite. And I hope everybody sees what I've done there. I didn't write FC this time, I wrote Fnet. Because again, I want to get you used to the fact that for circular motion, FC is Fnet. It doesn't matter what we call it. This is MA. This is GMM over R squared. And it's at this point in time, Ashlyn and everybody, that we say this is a centripetal acceleration. Okay? Where we go from now, this is the general strategy. The specific strategy, it branches off. Because when you look at your formula sheet, for how to calculate centripetal acceleration, because we're going to be doing a substitution, centripetal acceleration, which is in the center of the screen here, is V squared over R, or 4 pi squared R over T squared. And we need to be a little crafty and clever here about which one we're going to use. You know, on the one hand, I could do this, m times v squared over r equals g mm over r squared. Or I could do this. I could say m times 4 pi squared r over t squared, and I just want to make sure, did I get that right? Okay. Equals g mm over r squared. And again, I didn't mention it today, but I mentioned it yesterday. When I do satellite analysis, I don't write M1 and M2. I just write little m, big M. Little m is the satellite, big M is the central body tugging on that satellite so it moves in a circle. In this particular case, you're given the speed and asked to find r, basically, okay? So I'm not really too interested in using the formula on the right because, one, it doesn't have speed. Two, it has period instead. Could I use a different formula maybe to find the period from the speed? Well, no, I can't. You know, you might think you're going to use this formula on the right and just say, well, you know what, let's find the period from the speed, but the speed is 2 pi r over the period, and you don't know r. You're just going in circles here. Again, everybody, and then I'll get to the answer to the question. The formula on the right is only ever necessary if you know the period and want to find r. That's the only time you have to use that. So over here, what I'm going to do is I'm going to cancel the masses of the satellites. That's the mass of the satellite above in Jupiter's orbit, or in orbit around Jupiter. I can cancel as well one of the r's. In other words, mathematically, everybody, I'm just multiplying both sides of this equation by r. And r over r on the left cancels. R over r squared on the right cancels, leaving me an r on the bottom. And this will allow me to cross multiply. V squared times r will equal g times the mass of Jupiter. So r will be equal to g times the mass of Jupiter over v squared. Now, that's not going to be the answer. There's something else we have to consider. So I need to take g times the mass of Jupiter over v squared. G is known to us, 6.67 multiplied by 10 to the negative 11 times the mass of Jupiter was given in the question as 1.9 multiplied by 10 to the 27. Divided by that speed squared of 3.12 multiplied by 10 to the 4. Don't forget to square it. Just double check everything here. Again, you may not be as excited about this as I am, but this is pretty powerful stuff. As soon as Cavendish discovered what capital G was, you could do stuff like find the mass of the Earth with a simple experiment on Earth. And then knowing how far Earth is from Sun, and that's a different story as to how that's determined, but it can be determined, you can determine the mass of the Sun. Once you know the mass of the Sun, you can use celestial mechanics to determine the mass of Jupiter. Like it opens up the door for a lot of inquiry in science. So that's what I am getting for r. The only problem is that's the orbital radius of the satellite, but you're asked for the distance above the surface of the Earth. So again, a general picture that's not going to be necessarily to scale here is that this is Jupiter. This is the satellite's orbit. Kind of, right? What we have just found is this distance. This is r in the equations. What we want to find is this distance, and we know that the radius of Jupiter is, I didn't even really look at it, 6.99 times 10 to the 7. And what we calculated, there it is, was that this radius, the entire radius of the true circular orbit, is 1.302 times 10 to the, I guess that's 8 meters, which means that that question mark is going to be the difference between those two, which will be about 6 times 10 to the 7. Yeah. Is that okay? Any other questions? Okay, there are a couple of other things I wanted to discuss with you and show you. Because I said yesterday that this stuff opens up a lot of interesting ideas. One of the things we did yesterday was we did a calculation that involved the mass of the sun. And the mass of the sun is this many kilograms. And I told you that you have a very hard time with numbers this big, even imagining what that is. I mean, you know it's a big mass, right? But just talking about the number 10 to the 30, how big of a number is that? So I want to just show you a couple of things, and then we'll talk about something that arises out of geostationary satellites. Let's imagine that was not a number of kilograms, but it was a number of seconds. I'm just talking to you here about trying to grasp the enormity of a number that big. If that were a number of seconds instead, what kind of time is that? You know it's a long time, right? But how big is it? Well, we've done this before. We're going to do it again. I'm going to take that number, 1.99 times 10 to the 30. That's seconds. And again, I know it's kilograms because we're dealing with the mass of the sun, but I'm trying to impress on you how big of a number this really is. And let's divide by 60 to find out how many minutes it is. And I hope that everybody would agree I'm no closer to appreciating that length of time now that it's in minutes compared to knowing it in seconds, right? So let's divide that by 60 again, and that's the number of hours. Well, that's really not much more helpful, is it? Let's divide it by 24 to find out how many days it is, and it's not becoming clearer. The number is getting smaller, but it's still a staggeringly large number. Let's divide it by 365.25, which is the number of days in a year, so it's that many years. And I still don't have a conception of how big of a number that is. I guess the only other thing I could use is the age of the universe. And based on astronomical observations and based on physics, how many of you are familiar with this concept called the Big Bang? Well, we can trace portions of the universe. Not everything is moving away from a central point, but solar systems and galaxies in general are. There's some spiraling going on. But based on celestial mechanics and physics, they can predict at what point all of that stuff was together. And at that point, it wasn't stuff, it was mostly energy. It's very complicated. Big Bang cosmology. So I'm going to just show you age of the universe. I'm typing it in because I'm embarrassed to admit that I forget. I think it's about 15 billion years, I think. But I want to say 1.5. I think it's 15. Age of empires. Universe. I think it's 15 billion years. There are 13.7 billion years. 13.7 times 10 to the 9 years. So I'm going to take this number that's on my calculator, which is the number of years that this many seconds is, and I'm going to divide it by the age of the universe. And what I will be finding is how many universe lifetimes that is. And you know what? I'm still no better off at understanding how big that time is. It is vast if it were time. Now, I don't really have an analogy here for you for kilograms, but I will tell you, and this is leading up to Physics 30, that there's a process on the sun called fusion. And it's where all of the energy from the sun comes from. And in earlier grades, elementary, junior high, maybe even your Science 10 teacher said this, you're taught this mantra of matter is neither created nor destroyed, it merely changes form. Law of conservation of mass. It's baloney. Matter is destroyed. Matter can be destroyed. And I'm not just talking about doing this. That's not destroying matter. That's just rearranging it. I'm talking about matter disappearing from the universe. It's gone. And that's what happens in fusion. What happens in fusion and other radioactive processes, and you will learn in detail in Physics 30 about this, is that matter is converted into pure energy. It disappears from the universe. Mass goes away. And the fusion reaction that's happening on the sun, it's hydrogen fusion and among other things, means that matter on the sun is going away. It's disappearing. This mass today is less than it was yesterday. It's changing. And it's not just changing because it's blowing out into the universe, it's disappearing from the universe. Well, when we do this calculation in Physics 30, based on the amount of energy we can get from the sun, well, we're not going to do the calculation here because, and this isn't an insult, you can't follow it because you don't know about radioactivity. You don't know about Einstein's theory of relativity, all these things we would need. The mass loss of the sun per second is 4.3 times 10 to the 9 kilograms. It's saying it's 4.3 times 10 to the 12 grams, but I'm converting it to kilograms. So what we have is this mass of the sun, and it's losing 4.3 times 10, thank you, 9, to the 9 kilograms every second. Like in the time we've been sitting here, it's lost, well, what's it been, about 10, 15 minutes? 10 minutes times 60 seconds is 600. It's lost that mass 600 times. But yet, you know, every year they don't reprint data booklets and change this to 1.98 times 10 to the 30. Because that 4.3 times 10 to the 9 kilograms is it's a big mass, right? It's a huge mass, but it's nothing compared to the mass of the sun. How long would it take? Now, I think many of you understand that as the mass of the sun changes, the rate at which the energy is produced might change, and this number that it's losing per second is going to change. But assuming it kept up with this mass loss rate, how many seconds would it take to reduce to nothing? Well, let's divide the total mass by how much it loses per second, and we get the number of seconds. Well, we're not much better off than we were before, are we? You're talking about universe lifetimes. Other things are going to happen with the sun before it runs out of fuel. It's going to reach a point. It's very interesting, actually, and I'm going a little off topic, but I hope you'll remember some of these things for Physics 30. It's very interesting that we don't have the technology to build a fusion reactor on Earth, and the reason is you need to have the hydrogen moving incredibly fast so that it collides hard enough to fuse. It's a basic analogy, or a basic description. The problem is, in order to get it to be moving fast, you need a really, really high temperature. So anything we put the hydrogen in on Earth vaporizes. What's holding all the hydrogen together on the sun? I think we need something more specific than that. No, it's not the hydrogen that's holding it. Kind of. I don't know. I don't know what you have in mind exactly, Jay. No, it's not helium. It's gravity. There's so much mass that it's just held together in a nice compact sphere. It's hard to imagine, but the sun is vapor. There might be some, we suspect maybe there's a core to it that's maybe solid, but it's vapor. It's like, I mean, it's more dense than air, but it's basically a gas. As the mass of the sun decreases, the amount of gravity pulling it together gets less and less. And there's something called nuclear pressure, which is pushing all the gas out. All of these nuclear changes are pushing the gas away, but gravity's strong enough to hold it together. Well, if there's not enough mass, that outward pressure is going to win, and the star goes nova. Becomes maybe what's called a red giant. And there are other processes that stars can undergo. It could be that for some reason the nuclear process stops or slows down, and gravity is stronger, so it continues to get smaller and smaller. All of the gas is pulled closer and closer together. You could get what's called a dwarf star. Or if gravity gets out of control, you can get, does anybody know? A black hole. Where, let's not talk about why it's a black hole right now, but what does that mean? It means, it's hard to imagine, all of this matter goes to a point so small, it's tiny. Its dimensions, the actual, where all the matter are, could be a centimeter. And because of the intense concentration of matter, you get a really, really strong gravitational field. It's so strong, not even light can get out of it. And that's why it's called a black hole. That's pretty scary, that all that matter is just in this little, you couldn't put it in your pocket because you would immediately, as you got close to it, you'd be part of it, right? Because the gravitational field is so strong. So that was another thing that I think I wanted to talk about. And there's one more thing. Any questions about that? I'm trying to use the opportunity here to maybe instill a little more interest in science and physics. And, you can take a whole course in university on astronomy, which is a fascinating course. There's something else I would like to talk about, and that's a geostationary satellite. And a geostationary satellite, of course, we've got the Earth, right? And then at some distance, and can I get you to look back at the example from yesterday? And let's go back and let's look at this result that we got for a geostationary satellite. Unfortunately, I didn't write down the number. Can somebody tell me what we got for a radius? 4.2 times 10 to the 7. So just a quick kind of calculation here. 4.2 times 10 to the 7 divided by 6.37 times 10 to the 6 is about 6.5 times the radius of the Earth. Okay? So it's quite far out there. And this scale that I have here, whoops, that's not what I wanted to do. This scale that I have here is actually not too bad. Let me just make it bigger and then we'll check. So this is the Earth. Oh. This is the Earth. This is the orbit of the satellite. I don't know. What did I say? 6.5 times? That's 1, 2, 3, 4, 5. Yeah, it's pretty close. That's a rough estimate, okay? So what you're looking at here, everybody, is this is the North Pole of the Earth, and it is rotating, but the satellite is rotating. It's moving faster than a point on the Earth, but it's rotating at the same rate. So every 24 hours that goes around, that satellite will go around once as well. It's always above the same point on Earth. So people have this idea, and it's an old idea, it's from the 1700s, that if you have this satellite, I don't know, this is the satellite. It's in free fall. It doesn't require any energy to keep it moving, which is a weird idea. It might require some energy to correct its orbit over time. You know, there's a vacuum of space, so there's no friction, but every now and then little space particles hit it and slow it down or affect the orbit. But that's minimal. So people had this idea that, you know what we should do is we should very gradually add some mass to the bottom of it, and just to stabilize it, let's add some mass to the top. And what's important is that the center of mass of the satellite is at that altitude, and then the whole thing will move at that orbit. It's like the pig. We didn't care where the wing was in the flying pig. We cared where the center of its mass was. And they said, you know what, let's just, over time, let's make this a little bit longer, and let's put this is called a counterweight on the other side. Let's just continue to make it longer. Until eventually what you get is this. And by the way, in order to make this engineering feat even possible, what you would have on the end of this thing would be a counterweight. So you don't have to make this end of it very long. You can just have some weight on there. And this connects to the Earth, which means that it would be on an island somewhere. It's that if you were on the island, you could walk up to the thing and you could climb it. You could build an elevator and climb up to the top of that. This is called a space elevator. And get up there, and what happens is this: if this whole thing is spinning, as you get to a higher altitude, you start moving faster. You're moving faster horizontally speaking. And when you get to the top, if you just step off, you've already got the orbital speed needed and you're at the right altitude, you'll be in orbit. So the idea is that you construct this so that rather than using chemical fuel, which is very wasteful, it's very inefficient, you use other processes to move materials to the top, where you build a satellite and then you just kind of push it out the door at the top and it's in orbit. And if you didn't want it right there, you could use a little bit of engine power to move it to someplace else in this orbit. But then the idea becomes, and this is more science fiction, we're a long way from this, but if you're a reader of science fiction, there have been a lot of novels that have been written about this stuff, that you could take that satellite and really you could populate, I'm going to get rid of the elevator part, you could populate this whole ring with satellites. In fact, the ring around the equator at this altitude has hundreds of satellites that are all, I mean, they're not right next to each other, but they're all moving at the same speed, so there's no chance of them colliding. And if you can populate this with enough satellites, you can actually make a ring. You can actually make a ring out in space that is turning at the same rate as the Earth. Some people call it a space wheel. And that thing wouldn't require energy to keep moving. Now, why on earth would you do this? And you have to realize, first of all, people that are thinking of this are very forward-thinking. They're thinking tens of thousands of, maybe hundreds of thousands of years in the future. We need energy to survive. We do. Our fossil fuel is going to run out. Estimates vary, but 500 years from now, we cannot be relying on the fossil fuels. They'll be gone. And fossil fuels take millions of years to produce, so that's gone. We have to move towards nuclear. Solar and wind is just not enough energy on the surface of the Earth to keep us going. And we do calculations in Physics 30 that demonstrate that. We have to go towards nuclear. But even the fuel that we mine out of the Earth for nuclear is very, very limited. Well, not very limited. It's going to run out. Okay? Where is all of the energy in our solar system? It's coming out of the sun. And when you look at all of the energy that's hitting this region, very little of it hits the surface of the Earth. We have a problem with collecting solar energy as well because it's cloudy a lot of the time. So what you do is you populate this with solar collectors, solar cells. You see the big solar energy panels that are on buildings? Well, you just populate it with that. And no matter where the Earth is in its orbit, something is going to be collecting the energy. And we can beam the energy to Earth, literally beam the energy in the form of microwave radiation, and then transfer it back to whatever energy, electrical, we want to use. So it's a fascinating idea, but the stumbling block is, you understand this would be a monumental construction, right? It's not just, oh, let's start, okay, let's get some wood and some concrete and some iron girders and start building it. Because of the gravitational forces involved, this counterweight is important so the whole thing doesn't fall apart. By the way, you would only need to, once you built it, this would be the only place you would build it. You wouldn't need to build it everywhere. But the tension in everything that's supplying that force, keeping it in that orbit, because of the counterweight, those forces are competing. There's tension. You take a piece of spaghetti and you try pulling it, it's going to snap sooner or later. So the difficulty is finding a material that can withstand that stress. But there's people actually working on it, called carbon nanotubes or buckyballs. You can do your own research on that. Some very, very interesting things. In addition, it's a good way of launching objects out of the orbit of the Earth, because if you can move them up to this point where this counterweight is and let them go, they're moving quite fast, they will leave the surface of the Earth. That's Newton's cannonball, but moving very fast. So it's a way to launch satellites and spacecraft to other parts of our solar system. So I wanted to talk a little bit about that. And again, my motivation is to try to spark some interest in some of these things. Does anybody have any comments or questions on that? No?
I got something to say.
Yeah?
Well, did you hear about Elon Musk trying to make like light speed engine, but not quite?
Talking about the hypertube or the...
Whatever, it speeds up particles and lets them release, and it gives a certain.
Oh, is this the for launching? Is this the circular thing that I had mentioned a couple weeks ago? It's something different, eh?
Something different, and he said you could get to Mars in 12.5 minutes.
Wow. I'm going to do a little bit of research on that so that we can have a conversation on it without me just kind of guessing. The difficulty, and let's have a little conversation about that. What is the distance to Mars? Let's see. I think I have that information here. Don't I? Yeah. The distance to Mars would be the difference between this number and this number. And that would be in ideal situations where Mars and Earth were both on the same side of the sun, which you can't just snap your fingers and make that happen. But the distance would be that. Well, now, before we go any further, are you talking about with people on board?
Yes.
Okay. That's what I thought you were talking about.
It's supposed to be
Okay. So if I take 2.28 times 10 to the 11, I could have done this in my head, minus 1.49 times 10 to the 11. We're talking here about a distance of, what did I do? Thank you. I got it, yeah. We're talking about, let's just call it 8 times 10 to the 10 meters. So here's Earth. Here's Mars. We've got to go a total of 8 times 10 to the 10 meters. Was that what it was? Okay. Now, there's all kinds of ways we can analyze this, and I'm not saying he's wrong, but let's go with the 12 minutes. Heck, let's go with an hour. Okay? An hour is 3,600 seconds. Now, what would the average speed have to be? That's allowed. It's not faster than the speed of light. If you look on your formula sheet, the speed of light is 3.00 times 10 to the 8. This is about 7% the speed of light. Okay. Now, historically speaking, that's not possible yet. I don't know what he has in mind. And I know that a lot of people seem to think he's a crackpot. But he has some good ideas. He's not dumb. So it's doable. However, how are you going to get there in that time if your average speed is this? That means that you have to accelerate to at least this speed. This is an average, right? Which means you have to be going faster at times than you are at other times. It's like when I talked about Ben Johnson running 100 meters in under 10 seconds. That's 10 meters per second, but he has to be going faster somewhere to average out at 10 meters per second. So, I don't know what the plan is here for the acceleration, but let's just say that you are going to accelerate to that speed in half the time and then decelerate in the other half the time. I don't know if he wants a totally symmetrical trip in terms of physics, but let's assume that. What would your acceleration have to be to reach that speed that I have here of 2, let me get it back. It was 8 times 10 to the 10 divided by 3,600. This is the average speed in meters per second. And you want to reach that speed in half the time so that you can decelerate in the other half. Well, acceleration is change in velocity over change in time. If I take 0 to this, that's the change in the speed, divided by 1,800 meters per second, I get this acceleration. Now, this is an average. So, there are finer points in our analysis here. But how many G's is that? That's an acceleration in meters per second squared. Divided by 9.81 meters per second squared, that's over 1,250 G-forces. I shouldn't have to tell you what would happen to you if you were in that environment, right? You'd just be a puddle of mostly liquid, but some lumps of bone and stuff. Like, it's horrid to even think about. But I don't know how that would be physically possible. But I'm going to do a little bit of research. It's an interesting idea. If there are no people on there, then that's a different story. The back of my head, and I can't quite wrap my head around it enough to justify this, but in the back of my head I'm thinking, since it's not survivable with averages, we can't cheat the system and bring that down at other times. Because if we bring the acceleration down to survivable, manageable limits, in order to get that same time, you have to bring it up somewhere else. That's just kind of common sense to me. In 1979, 78, NASA launched a number of spacecraft called Voyager. Are you familiar with that? Or if you're a Star Trek fan, V'ger. Ever seen Star Trek the movie? No? I may have just ruined the whole movie by telling you that. Sorry. And I don't mind blowing off a whole class talking about this. I don't. I think it's just as valuable as anything we learn in terms of the curriculum. Fastest man-made object. It's probably going to be Voyager, spacecraft. Actually, it's not Voyager. So, the fastest human-made objects are spacecraft. They use rockets, et cetera, et cetera. The spacecraft that is traveling the fastest so far is NASA's Parker probe, and it has reached a speed of 535,000 kilometers per hour. That's accelerating for 4 years, and it's only at 0.05% of the speed of light. I mean, the other thing we have to understand is you start looking at an acceleration of 1,250 Gs or whatever it was, or 12,500, I can't remember, 1,250 Gs. Never mind humans being able to withstand those forces. What about the spacecraft itself? That means that the back of the spacecraft is pushing forward on the front of the spacecraft with the equivalent of 1,250 Gs. So the nose of the spacecraft, if you want to think of it that way, is experiencing 1,250 Gs. I don't know what you can make that can withstand those forces. So, I'm skeptical of his claim, but he has said some crazy things before. It's kind of like, do you remember when I started this unit and I talked about I forget, there was a name for it, that rotary launcher that they would put something in that big centrifuge and they would just spin it faster and faster and faster and then spit it out? I don't know how the objects could withstand those forces. Those centripetal forces, or those net forces applying the inward force of them, are too vast in my mind for objects to withstand them. I'm going to do a little bit of research with that. I do want to hand out assignment number 4 here. It's a satellite problem that is due on Monday. And I want to remind you that for assignments, now that we're at this point in the course, they're done with a level of sophistication that says, I'm taking high school physics. Like almost post-secondary sophistication, that you're showing all of your formulas. You're explaining why you get a certain formula. It's not just writing down a formula from your notes and throwing the numbers in. You need to show all of your work and explain all of your work. So it's a single satellite problem where you have to determine both the speed of the satellite and the orbital period of the satellite in minutes. Your pig lab is due tomorrow. However, we are moving on tomorrow to something else, so I will say that your pig lab I'm going to take in on Monday with this written response assignment. Okay? So tomorrow we start fresh with a new chapter and a new set of ideas dealing with energy. You're welcome. You still have about 25 minutes in class. To work on those 2 tasks. If you feel you need extra practice with satellites, you have those textbook questions as well that were outlined. In your handout. Of course, yeah.